Hello, this is Lab 3, Black Hole and Orbits. So pretty much this lab, to preview system, it varies on the parts of the lab, and the main forces that we are considering is gravitation and its influence on net force and momentum. So the purpose of the lab is to find the mass of a black hole in part 1 by analyzing the motion of an orbiting star. And for part 2, we're going to be able to find the initial velocity that a spaceship has to obtain to not crash into the given planet. And the key assumptions that we're making in this lab is that we are ignoring all other outside forces besides gravitation and in its resulting calculations. So the key concepts we'll be using in this lab include Newton's universal law of gravitation, which is F equals G mass 1 mass 2 over r squared, and Newton's second law, the momentum principle, which will be net force, which is the derivative of momentum. So since we have the mass of the star in the black hole, we're going to rearrange the formula. I'm sorry, the formula includes the mass of the star in the black hole. We'd be able to rearrange the formula to solve for the mass of the black hole. And by splitting the momentum principle into its vector components, we're able to get a formula that uses parallel and perpendicular components. So for the procedure, using the information they give us in part 1, we're going to calculate the mass of the black hole, and we're going to use GlowScript to model the motion of the orbit around the black hole. And for part 2, we're going to substitute necessary formulas and use trial and error to pretty much, figure out the initial velocity of the ship. And also use GlowScript to model the motion of the orbit and form conclusions and answer discussion questions. So part 1, where we're finding the mass of the black hole, this code is pretty much rearranging the universal law of gravitation to find the mass of the black hole, isolate that. So set M2 or M1, whichever, or M1 equal to, that would be G times M2 over R squared and force. And the part 1 results, since the orbit isn't a perfect circle, the mass is different at every time step. However, at the end of the orbit, the mass was 1.1735 times 10 to the 34th kilograms. In part 2, we were essentially trying to find the initial velocity of the spaceship that was needed in order for it not to crash into the planet. This is the code that was pretty much used in this. And for this one, we split the momentum principle into its different vector components to be able to use parallel and perpendicular components to find the initial velocity. So as a result, some possible errors that could happen is there was inaccurate approximations of data. So since it was a simulation, it may not represent reality. And there also could be other outside forces impacting the system that we did not realize. So through multiple trial and errors, the model established that the spaceship's initial velocity for it to not crash into the planet would have to be negative 2.9 times 10 to the 4th in the x direction, 2.9 times 10 to the 4th in the y direction, is 0 in the z direction, and that's meters per second. So what this means is they're the same mathematically, but the change of momentum is easier to measure because we only need to know the system's change of velocity. What if the system had a black hole, a star, a planet, and a moon? What would you need to include in your computational model to predict the motion of the entire system? We would pretty much have to include the masses of all the objects in the system and recalculate the net force, as it related to the black hole. And yeah, that is my lab 3.